Hi everyone, my name is Muyang, and today I'll be presenting our work on modeling human actions with Neuro Symbolic Relational Planning Models. In human-robot collaboration, robots and humans take actions in parallel to complete a task. In order for the robot to plan its own actions to best assist the human, it must be able to model the human's behavior at a high level. What actions will they perform in a given state? And what effects will those actions have on the resulting state? Deep learning-based approaches have been proposed for answering both of these questions. Human action anticipation seeks to predict the future actions a human will take, while latent scene dynamics models can be trained to predict the next state from a state-action pair. These methods are robust to noise and can handle unstructured data like images. However, they require a large amount of training data to generalize well, and as black boxes, they lack interpretability, a crucial quality in human-robot collaboration. To address these issues, we propose Neuro-Symbolic Human Action Models, a novel approach to modeling human actions that combines learned symbolic knowledge with neural networks. On the symbolic side, we learn a probabilistic planning model with explicit preconditions and effects, similar to a PDDL spec. On the neural side, we learn two neural network models, a next action anticipation model and a relational scene dynamics model. Neuro-symbolic human action models integrate these neural and symbolic components to form a comprehensive model of human actions. The neural component improves robustness to noise and allows the use of unstructured context, while the symbolic component enables learning from scarce data and adds human interpretability. We evaluate the performance of our method on a real-world human action dataset, demonstrating its advantage over purely neural or symbolic ablations. Now let's dive into the methodology. Symbolic planning models are used in automated planning to describe the preconditions and effects of actions. For example, the precondition of a person sitting in a chair is that the person is standing and a chair exists in the scene. Standard planning model frameworks, such as PDDL, assume the environment is deterministic. However, in the real world, actions do not have deterministic effects, and since we're modeling an external agent instead of planning, we must also account for the fact that an action being feasible, its preconditions being satisfied, does not guarantee that it will be chosen by the agent. To quantify this uncertainty, we assign a probability to each precondition and effect. Firstly, given that a precondition of an action is satisfied, what is the probability that that action is actually taken? Secondly, given that an action was taken from a certain state, what is the probability that a certain effect actually occurs? Our method uses a relational abstraction of the state in the form of a scene graph to enable symbolic learning. In this representation, nodes represent objects and edges represent the relationships between them. This can be obtained using off-the-shelf scene graph generators. In this work, we assume scene graphs are given as input. So, how is the symbolic planning model actually learned from transition data? We employ inductive logic programming, a common tool for symbolic learning, to learn actions, preconditions, and effects. ILP is a class of rule induction methods which, given a set of positive and negative examples, searches for a rule which succinctly entails as many positive and as few negative examples as possible. For learning preconditions, we group transitions by action and formulate one ILP instance per action. For learning effects, we first compute the differences between the pre- and post states in the transition, and then group by added and deleted relationships. We formulate two ILP instances per relationship, one for the case where that relationship is added and one for when it is deleted. Importantly, we use an ILP system which can handle noisy examples and compute the probabilities of preconditions and effects based on how well the rules fit the data. For more details, please see the paper. Now I will introduce our neural pipelines for next action and next state prediction. For next action prediction, we take an image and scene graph as input. Each modality is passed through its corresponding feature extractor, followed by an MLP to produce the final prediction. For visual feature extraction, we use a multi-scale vision transformer. For graph features, we use a relational graph convolutional network. Once symbolic models have been learned, we can integrate them into the action and state prediction pipelines. For next action prediction, we evaluate the preconditions to get probabilities for each action, and multiply these with the neural pipeline output to get our final prediction. The next state prediction architecture is similar, except instead of a single action classification, we do pairwise edge classification and combine with the symbolic effect probabilities. We evaluated our Neuro-Symbolic Human Action Models on the Action Genome dataset, which contains over 80 hours of action and scene graph annotated video of humans performing various indoor activities. We extracted state, action, next state transitions to train and evaluate our models. Preliminary results show that our neurosymbolic approach outperforms purely neural or symbolic ablations across all metrics on next action prediction. We also compared against a recent multimodal vision language model, which performed poorly. Looking into the confusion matrices, we see that the predictions are very different for the symbolic and neural components. Notably, the learned symbolic planning model obtained strong rules for rare actions, which had very few positive examples, whereas the neural pipeline alone barely predicted rare classes, but performed well on common classes. Thus, their integration yielded more balanced predictions. Next state prediction is currently still being evaluated. In the future, we plan on employing neurosymbolic human action models in a simulated multi-agent human environment to validate their utility in human-aware task planning. We would also like to look into better ways of integrating the neural and symbolic components during training time. Thank you to my wonderful mentors, Professor Katia Sycara and Professor Simon Steputis, and to the RISC program organizers, Rachel Burson, Dr. John Dolan, and Maren Landis.